This is Edx Further Maths Core Pure. We're in the second matrices section and on the fifth video on transformations in 3D. We need to consider a couple of simple families of transformations in 3 dimensions, and those are reflections in each of the planes defined by x equals 0, y equals 0 and z equals 0, and rotation at just multiples of 90 degrees about one of the axes. In general, finding a 3D matrix for a transformation is very similar to finding one in 2 dimensions. We simply need to work out where the points 1, 0, 0, 0, 1, 0 and 0, 0, 1 go to when the transformation is applied. So I'm going to call this my point A, this my point B, and this my point C. So these points in 3D space, if I just do a quick sketch, there's my x-axis, there's my y-axis, and we always have a right-handed set for our axes. So if my right hand, if I put my thumb along the x direction, the positive x direction, my first finger along y, then my second finger will give me the direction of the z-axis, and then if I mark the points on each of these, this one will be A, this one will be B, and this one will be C. So what transformation does this 3 by 3 matrix represent? We can think of this when we apply this matrix. So here's the matrix. To apply a matrix, we simply multiply it by the object that we're trying to transform. So I'm trying to transform my matrix made up of the points that represent A, B and C. Since that's the 3 by 3 identity matrix, I simply, quite trivially, get M as the image of these points. So this is point A dashed, this is point B dashed, and the column there will be point C dashed. And we can see in this case that B and C haven't changed, but the point A has changed under this transformation. If we take a look here, a nice way to look at this is to look in 3D at the transformation of a unit cube. So the brown cube is the initial unit cube, and I've transformed this with the matrix M to make the green cube there. And you can see that the point B remains unchanged and the point C remains unchanged, but the point A has been transformed from there over to there to minus 1, 0, 0. And you should be able to see that this is a reflection. And how would we describe this reflection? It's a reflection in, we could call it the YZ plane, which we could also refer to as x equals 0. So that's a nice way to view that. Here's a second example. This looks a bit more complicated, but again, here's our image of A, our image of B, and our image of C. C hasn't changed, but A and B have. And if we take a look at this here, that's very similar to a matrix that we're familiar with from 2D transformations. And this was a rotation of 180 degrees in 2D about the origin. In this case, our Z remains unchanged, so this matrix represents rotation of 180 degrees about the Z axis. So here again, I've done the same thing again. I've taken the brown cube and I've transformed it using my matrix M. We can see that the point C is the only point that remains unchanged here, but hopefully you'll be able to see that A has rotated to A dash and B has rotated to B dash, which is a rotation of 180 degrees about the Z axis. There are more notes in Integral about 3D transformations, And it's always nice to use an application like GeoGebra to try to investigate these for yourself. That's the end of this short video, and the next video in the series is on invariant lines and points.